beams. Bhaskar, the stage is yours.
Thank you. So I will share the screen. Yeah, so I hope you could see my screen.
Yes, we see a Google search right now.
You
Yet
don't
to
see my
see your slide.
presentation?
Now we see it. Now we see it. I see your slides now.
Okay, perfect. Okay, so first of all, thank you very much for this kind introduction, and also I would like to thank the organizers of this school for giving me this opportunity to discuss some of our experiments or some of our research in the direction of partial coherence and quantum optics. So my name is Bhaskar Kanseri, and today I will be talking about partial coherence and quantum features of light beams. So before I go into the actual work, I would like to just tell about our group at IIT Delhi. So our group is named as Experimental Quantum Interferometry and Polarization Group, and we essentially work in two domains, broadly in coherence and polarization optics, which is more of classical optics, and also in quantum science and technologies, which is one of the most recent or most well-cited topics nowadays. So in classical coherence and polarization, our interests are to work on coherence polarization engineering, to demonstrate electromagnetic beams experimentally, and I'll just switch on the pointer. Yeah, and to work on different type of coherences, such as one of the recent ones is the longitudinal spatial coherence, and also to show their applications, for example, in spectral manipulations. The other activity in quantum science and technology, we have been working in some of the fundamental areas, such as how coherence and entanglement are related, on engineering quantum states of light, on looking their applications in quantum secure communication, in quantum imaging, and very recently we have been more involved in fiber and free space QKD as well. And these are some of the funding agencies which have been supporting us during these experiments. So today, the plan of talk is as follows. I will briefly discuss, I will start with the classical coherence. We'll discuss what is polarization, what is coherence of light, and how one can unify them. And then one can actually engineer the polarization and coherence properties of light. And we will show you that there could be actually having several applications, not only in the area of classical optics, but also in quantum domain. And then I will be discussing about partial coherence and how we can actually use it for quantum secure communication, and some of our recent activities in the area of photonic quantum technologies, and finally I would summarize my presentation. So let us begin with some of the, I think, one of the well-known topics in the area of coherence and polarization, so polarization of light. And we already know that it is given by the orientation or the trajectory of electric field vector. So it is shown here in linear polarization. One can measure the polarization features by Stokes parameters, and we call them usual Stokes parameters now because we have a generalized Stokes parameters also, which I will discuss in a while. So in Stokes parameters, we have four parameters given by, the first one given by the total intensity, then we have linear and 45-degree linear polarizations, and then circular polarizations. And in fact, these parameters are fully describing the polarization features of a light beam in first order of intensity. One can actually write these Stokes parameters in a way that one can define the degree of polarization, which is essentially the ratio of the polarized intensity with the total intensity, which consists of the polarized intensity as well as the unpolarized intensity. And this gives us an idea of a three-dimensional sphere, which we call a Poincare sphere, where one can actually represent different degrees of polarizations of light. So we already know that on the surface of this sphere, we have all linear polarizations, which could be actually 45-degree linear or horizontal and vertical in the equatorial plane. And as you move from equator to up and down, we actually come up elliptical polarizations, and at the poles we have right circular and left circular polarization. However, if we go inside that sphere, we are essentially decreasing our degree of polarization, and we can have again spheres inside which are having the center as the origin, and all these layers have different degrees of polarization, and as we reach in the origin, we have actually a degree of polarization 0. That means the light of which is unpolarized actually sits in the center, and all other inner area is basically partial polarization of light. So polarization is a single point property. On the other hand, if you talk about the coherence, coherence is essentially the measure of correlation in phases between time and space points of the optical field. And I believe that all of us are aware about these two coherences. That is a temporal coherence, which is essentially given by the correlation between two different time points, essentially it is governed by the monochromaticity of the source, and the spatial coherence, which is given by the correlation between two spatial points at the same time, and it is actually defined by the dimension of the source. So it is a 2-point parameter, unlike the polarization. One can actually measure the degree of coherence, which is given by the visibility of fringes, or it actually defines that what kind of interference fringes this coherence is able to produce. So if the degree of coherence is 1, we call the field is fully coherent. If it is 0, we call it is completely incoherent, and any value in between 0 and 1 is basically the partial coherence of light. One alternative way by which one can define the coherence of different polarization components is given by a coherency matrix, which also call it sometimes polarization matrix, and each component of this matrix is essentially giving us the correlation between the electric field components. For example, this is between X components, this is Y components, and this is XY and YX components. So it is a 2x2 matrix, and essentially this matrix defines the properties of polarization. So it is a coherency matrix, but it also defines the properties of polarization. So one can define, for example, the degree of polarization by this equation, where this 4 times the determinant of this matrix divided by trace of this matrix whole square gives us actually that what kind of degree of polarization is here. And that degree of polarization can be actually also lie between 0 and 1. When 0 means it is completely unpolarized light, 1 is completely polarized, and any value in between 0 and 1, we call it partially polarized light. So we could see there are several similarities between coherence and polarization, and essentially from this matrix, one actually deduces that the degree of polarization of the field is given by the maximum value of degree of coherence between the orthogonal set of field components having equal intensity. So there is basically what we could understand from this discussion is that the coherence and polarization both are essentially the manifestation of the same physical property, that is the correlation between fluctuations of light beams. One coherence, whereas gives us a 2-point property, so that is that measures the correlation in fluctuations at 2 space-time points, whereas the polarization measures at the same spatial point but at 2 different field components. So now, if we look into a Young's experiment, which I think was well explained in the previous talk, and I would like to see that what happens to the interference when we are interfering different polarizations of light. So for example, if we see here, this is a simple Young's experiment, a double slit, P1 and P2 are the 2 slits, and we are looking into the interference. So if we have X polarized beams, so P1 is also X polarized, P2 is also X polarized, and we get an interference fringes here, which are basically intensity fringes, and by measuring these visibilities of these fringes, we can essentially talk about the correlation between P1 and P2, and this is true for scalar optical fields. Now, if we have the same experiment, but now at the 2 pinholes, we have different polarizations. For example, at P1 we have X, whereas at P2 we have Y polarization. So essentially, as the polarizations are different, the electric fields are orthogonal to each other, and we will not get any intensity fringes. But it doesn't mean that there is no coherence between P1 and P2. The correlation still exists, but the interference which was earlier in the intensities of light is now in the polarization domain. So one can say that the interference is in the form of polarization modulations, and one can measure the visibility in polarization, which essentially tells us about the correlation between P1 and P2 again. So if we combine these two, that means we are talking about the fields which are electromagnetic in nature. So they are partially coherent and partially polarized, we call them. Then we have at both the pinholes, we have both kind of components. So we have electric field X component as well as Y component, and similarly in the other pinhole as well, with different proportions. So in that situation, whatever comes out as interference would essentially cover both intensity fringes as well as polarization proportions. So that means we have to actually keep intensity fringes as well as polarization fringes in the same focus in order to understand the correlation properties at P1 and P2. So for such kind of things, these coherence matrices, which I earlier told about, or the Stokes parameters, are no longer a single point property, but they are generalized into 2 points, and they are called as cross-spectral density matrix and generalized Stokes parameters. And in case of this unification, and this is the kind of unification where we have unified both coherence and polarization, and these 2-point parameters are the ones which actually give all the information about the field once one could measure them. And in past, we have been working on this area extensively since my PhD days. And there is a book where we have summarized all the experiments which we have done in that domain. And we have also seen that there are a lot of applications of this area in the domain of characterizing natural light sources or light propagation studies. For example, if you want to determine the cross-spectral density matrix, which is one of the basic or more fundamental ingredient here, which is given by this matrix mathematically. So here you could see that we are not only looking into the correlation between two space points, but also into different components of the light. So we have Ex with Ex, Ex with Ey, Ey with Ex, and Ey with Ey. So this kind of matrix can be measured experimentally, and we were the first one to demonstrate it by using an interferometer, which is we call as modified version of the Young's interferometer. So here is the interferometer, as you could see. As we know that in a classic Young's experiment, the slits are very narrowly separated. I mean, few microns, a few tens of microns, or few hundreds of microns kind of separations are there. So one could actually not having a liberty to control the polarization features of the interfering beams. So here you could see that we have an additional geometry here, where we separated these two pinholes, the light coming from these two pinholes. We have separated them enough so that we could put the polarization components there, and then mix them back, and then we could get the fringes. So these are the interference fringes which we get for different orthogonal polarizations. First of all, as you could see that if we have polarization same, we get intensity fringes. We have orthogonal polarization, we do not have any fringe. So this kind of experiment essentially are the ones which are having a lot of pedagogical applications. In fact, some of our work has published in those journals as well. And these are called the Fresnel and Arago laws, interference laws, in general for showing the interference, the dependence of polarization in interference. So here, by measuring these visibilities, we can actually measure the correlations or these components of the light beams. So I will not go into the detail of that, but I would like to talk about something which is of the interest of today's talk, that is the tunable degree of polarization. So as I told you that whatever in the Poincare sphere, whatever we were doing at the moment was with degree of polarization 1. That means we were only on the surface of the sphere. But when we go inside and we want to play somewhere in that three-dimensional space inside, so how to do that? So for that, we first thought to make a tunable degree of polarization source. So this is a typical Mach-Zehnder kind of assembly, and I believe you are aware with Mach-Zehnders. However, what we have done that we have moved one path, which is a translated, so that the paths could be varied. So we can actually interfere. That means the two beams in different times. Now the first one is a PBS, polarizing beam splitter. So again, the two paths which are interfering are having orthogonal polarizations, and by controlling by putting these components, we can actually remove that degeneracy, and that way we could get the interference fringes. So if we do the treatment for this kind of interferometer by using the Stokes parameters, so it is Stokes parameters means it is not only having intensity modulations, Now, intensity modulation here is given by only S0 parameter, which is basically the intensity filter. But we are also having Sn, that means other 3 parameters also, which are having the polarization information. So it gives us the total information about the interference, and that's why it is called the electromagnetic interference. So if we do that, we define 2 quantities here, which actually are giving us the information about whether the paths are distinguishable or whether they are indistinguishable. And that is defined one as the first Stokes parameter, which is called distinguishability. And it tells that whether this X polarization and the Y polarization, they are having same intensities or different. If they are having same intensities, we cannot differentiate between them. And then whatever comes out as an interference is given by only the visibility of the fringes. And this is the visibility, the way it is expressed. So visibility refers to the interference property, whereas the distinguishability refers to the which path information.
Sorry, Bhaskar, ignore it. Sorry. Yeah.
Okay. So there is no question.
Sorry, ignore it. Yeah. There is no question. Yeah, please ignore it.
Yeah, so we are talking about here the distinguishability. This gives us the information whether one intensity is higher than the other, or to distinguish between these 2 intensities. And if we could have equal intensities, then that means that we will be interfering the beams, and we have the visibility which comes into, which gives us the quality of interference. So we can have 2 possibilities. So first of all, the degree of polarization is written in terms of these 2 quantities, where gamma xy tau is essentially the correlation between this x and y component of the fields with different times. So tau equal to 0 means the 2 paths would be equal, otherwise the paths would be separated in time. And so we can have 2 situations here. First of all, we could have a situation when the fields are indistinguishable. That means the intensities are equal, or the first Stokes parameter is 0. D is 0. In that situation, this degree of polarization is governed by only the correlation between these 2 orthogonal field components with different times. So you could see here in this plot, we are plotting 2 situations. We are plotting in x-axis in terms of the value of gamma xy tau, which is basically the visibility of orthogonal field components, and in the y-axis it is the degree of polarization for different values of the distinguishability. So if distinguishability is 0, then there is this line which comes up. That means by controlling the correlation, we can actually control the degree of polarization. The other possibility is when the fields are uncorrelated. That means this gamma xy is 0. There is no correlation between x and y components. And in that situation, the degree of polarization can be controlled just by the first Stokes parameter. That means by the difference between the intensities. So if one beam is having higher intensity than the other, obviously the degree of polarization will be higher. And you can also see that in this case for different values of S1. So we try to do these 2 things experimentally. The first, we make a degree of polarization source with indistinguishable fields, and the same experimental scheme has been used. We are using a laser beam, and all these are different components written as quarter wave plates. CCD this is the one where we are looking into the fringes. And so what we found here, you could see that for the path difference, so when we are changing the path, essentially we are controlling the correlation between the orthogonal field components, that is gamma xy tau. So you see that gamma xy tau decreases as we have increase in the difference of path, and similarly also the degree of polarization decreases. So there is some dependence between these 2. And what that dependence is, you could see here that for different correlations, we could see that the degree of polarization also changes. So this is a tunable degree of polarization source with control in the path in one arm of the interferometer. And these are the different Stokes parameters, that how they vary when we change the path difference. This is one of the way. However, this is more complicated because you have to change every time the paths. So the interferometer may be misaligned and you have to align it separately. So it is much more complicated. But it gives a way to control that in terms of the correlations. The other possibility is the uncorrelated fields, and here we could see that we could actually have an interferometer where the initial laser is randomly polarized. That means you can, for experimental purposes, we can consider it as unpolarized. And then in this interferometer, we have 2 paths where we are controlling the polarization of one path, which essentially means we are favoring one intensity over the another. And you could see that when the intensities, when we change this angle, we are actually favoring the intensities, and that way the degree of polarization increases. So this beam splitter here can have a polarization dependence, and experimentally we found that it is quite non-ideal to have such kind of beam splitters. So we have to make allowance for that, and when we do that, the degree of polarization comes out to be quite complicated. However, it fits perfectly with the experiments. So in nutshell, we have a source of variable degree of polarization. Why we are doing that? So we already know that wave particle duality is a concept which is coming from the quantum mechanics or quantum physics. However, can we look into such kind of similarity of wave particle duality for classically optical systems? And one of such proposals were given by the Eberly group in Rochester when they proposed a polarization coherence theorem, where they say that the visibility, which is essentially giving us the, which is coming from the interference fringes and giving us a wave property, and the distinguishability, which is coming as localization of the paths or more as a particle nature, are actually related with each other, and the relation is controlled by the polarization. So it means that by controlling the polarization, we can actually control the wave particle duality. So if this is true, the question is, can we look it in a classical system or the system which we are working on? And in fact, we did it, and this was the first experimental observation of this polarization coherence theorem. And it essentially tells that the more and more phenomena or observations which were essentially considered as quantum properties are having there some equivalence in classical as well. And basically the boundaries between quantum and classical systems are becoming fuzzier or becoming or essentially merging. So this is the experiment. We had a variable polarization source by which we are controlling the polarization. As I mentioned that we have a control in degree of polarization P, and we want to see that how B and D are varying. And if we can have a control on D as well, we could see that whether by controlling P and D, we can get the values of V which exactly fit with this equation. So this is what we are doing. So this is the control in degree of polarization by which we are controlling the P. This is a PBS with a halfway plate, which essentially controls the one path with respect to another intensity, which is basically the distinguishability D. And what we are looking here are the interference fringe visibility, which is the P. So all three parameters we can have, and these are the results. So this is the result corresponding to, this is a theoretical picture of how all these parameters vary in 3 dimensions, and these are the points where we actually took the measurements. And these are the fringes which we get, and this is the nature of the fringes. So what exactly we get? For a polarized beam where the polarization is nearly 1, you could see that the change of V and D can be shown here by these points, and their square sum is always given by the P square of the light. If we have an unpolarized case, which where we experimentally we do get a polarization of degree of polarization of nearly 0.00 something, and you could see here again that the P square is exactly fitting with how the V and the D square are varying. And for an intermediate value of P as well, you could see that the variation are always complementary. So this is basically the complementarity of Bohr, which was also underlined in the previous talk, which we have seen for classical system. And for a very arbitrary case also, you could see that they are always perfectly fitting. So essentially what we are saying here is that when we have observed this wave particle duality with polarization of light as given by this equation, this polarization coherence theorem. In fact, later on, that group has also demonstrated that the polarization can actually be written in terms of entanglement, and actually what controls the whole picture is the entanglement. So P square plus V square plus C square equal to 1, and that C, that the concurrence or the entanglement essentially controls the wave particle duality. We have been using these tunable sources of light for several applications. For example, you could see here, this is a source which we made with tunable coherence as well as polarization. So this was the tunable polarization, and you could see here that the polarization was changing from 0.2 to 0.98 with a control in the wave plate. And we also placed a telescope here with a variable geometry, so that we could change the size of the beam, which essentially is focused on a diffuser which is rotating and making the beam incoherent. And then with propagation, the coherence increases as given by the Wenstedt-Nikke theorem. So basically, by controlling the size of the source at the diffuser, we can control the visibility of the beam. So this kind of source is essentially doing both jobs. We can control the polarization as well as the coherence properties of light. And you could see that we have a coherence control from 0.4 to 0.83, which is way enough in the partial coherence domain. And the purpose of this coherence control was for some of our experiments, which I will discuss in coming slides. Now, one thing which I already mentioned that was a non-ideal.
Bhaskar,
Yeah.
sorry, can I ask a question here?
Yes, please.
This is a bit curious. So when you say particle, what is it that, I mean, I could not appreciate probably. So you mean if the beam is very localized, then you will call it a particle type, and if it is very delocalized, then you will call it a wave type? Is that the idea?
Yeah. So the idea is that if we know that, so we have two beams which are interfering. If we know that if the two beams have equal intensities, we cannot differentiate the two beams. We cannot differentiate which path the beam is traveling. So which path information is zero. And what we get is the maximum visibility in the interference. Now, I am preferring one beam over the other. I am controlling the intensity in such a way that one beam is intense with respect to another. So that I can easily know that from where the light is coming more with respect to the other. So that means my interference visibility will decrease, which is a wave nature, and my particle property will increase. That means I will be able to localize that which path the beam is coming.
Okay, so can we say that that's pretty much like a Fourier transform rather than a, sorry, this is just maybe I'm just not comfortable with the concept. So is it like a Fourier transform thing? See, I mean, even in
Fourier transform,
say that the momentum and coordinate are kind of not conjugate, but some kind of conjugate variables, right? So in that sense, even in classical physics, I can see reflections of that without H-cut playing any role.
Yeah, so this is all classical. What I am talking about.
That's what I'm wondering. Oh, yes.
There's nothing quantum so far. I'm just talking about classical.
Nothing quantum.
Yeah. I'm saying that what we see in case of quantum has already an analog in coherence and polarization domain, and that was the interference and this distinguishability and visibility which I mentioned. So there is nothing quantum here. I will talk about quantum aspects maybe in next after a few slides.
Okay. Thank you.
Okay, fine. Yeah. So I will talking about
thanks.
non-ideal nature of beam splitters, so, and which is one of the big concern for experimentalists. The reason being that if beam splitters, that is 50-50 beam splitters, for instance, which are not supposed to have any polarization dependence, do have some polarization preference for transmission and reflection. For example, see the transmission and reflection of one practical beam splitter which we have. Ideally, this should be 50-50. But you could see that the transmission for Y has 0.55 and transmission for reflection for Y was 0.44, and it was even worse in case of transmission. So that means that all our experiments would be modulated due to this polarization dependence, and that's what we have seen experimentally as well. So we started with a vortex beam. So it is a kind of beam which has an intensity 0 in the center. We also call it sometimes donut beams. And these beams can be constructed in the lab by using different type of optical components. For example, a Q plate or a wave plate with some polarization sectors made in such a way that at the center it gives us a 0 value. So this is an experiment where we used such kind of beams, and what we found that if we look into the intensity pattern of the input, for example, so this is the intensity, we have intensity 0 and then we have higher intensities in the sides like this, and the polarization was homogeneous, so everywhere the polarization was same, and also the phase was something like that. And when it transmits and reflects from this kind of non-ideal beam splitter, you could see that in the transmission, the intensity gets slightly changed in its shape, whereas it has some value of depolarization which is introduced in the center, which is much more pronounced when we have a reflected component. You could see that the intensity has drastically changed. At the same time, the polarization is completely inhomogeneous. You could see that the polarization is somewhere maximum, somewhere even 0 in the axis. And so far we are not doing anything in the experiment. We are just passing it through a beam splitter. So you could see that one can actually get such kind of weird results even with a beam splitter which is having non-ideal characteristics, especially when working with coherence and polarization. And they become problems with vectorial beams, as I have shown, such kind of vortex beams, and also in quantum domain. So one needs to actually look into these aspects and characterize them well before doing any experiments. Okay, now I would like to go to the quantum domain. So experimentally, we use a process called spontaneous parametric down conversion, which is used to generate these pairs of photons, which we call signal enablers. And in the previous talk also, they have been using such kind of geometry as well. So here, what actually happens that a beam which is having a very high intensity passes through a nonlinear medium, which is a QIQT medium we call, and it gives birth to a pair of photons provided to the momentum and energy conservation relations. So these photons are correlated in numbers, they are correlated in momentum and position. And also the process is actually given by this wave function where always there is a pair generation happening. And these constants C1, C2, actually there should be a constant here as well, C1, C2, C3, all these constants are actually given by the Hamiltonian and the interaction strength. So by controlling, for example, this chi2 of the medium, the length of the medium, and the energy of the pump, one can actually enhance the generation of these pairs. So we can have even more higher orders or we can have less order depending on the interaction strength. So if we want to generate bright beams, we need to have very high parametric gain. That means we need to use pulse lasers. We need to do a lot of very high energies in the input. If we want to have single photons only, then we need to have a low parametric gain by which we could actually cut this series somewhere here. So we have no multi-photons and only vacuum and single photons. And that's what we use for several cases. For example, for the single and in order to make the entangled photon sources, one could actually use this process with very low parametric gain. One can have only pairs, so one can detect one out of the pair so that we herald another photon as a single photon, and that can be used for several applications. One can actually make two photon entangled states, and this is one example of such a state which is actually violating the Bell's inequality, and that's why it is called a Bell state. You could see that it can have, it can be in two modes, A and B, and two polarizations, horizontal and vertical. So, for example, if this is the source which is generating these two modes, which can be, for example, frequency modes or spatial modes, then if one of the photon is detected by a polarization splitter in horizontal domain, that means it is horizontally polarized, then the other would always be detected as a vertical polarization because this is the way the state has been prepared. So there are always correlations which are anti-correlations in polarization, and irrespective of whatever be the distance between them, the quantum entanglement persists, and all these correlations will be obtained. So this kind of entangled photons are used for several applications. So I would like to show one of the applications where we use partial coherence and how SPDC can be modulated with partial coherence. So when we say partial coherence, we are essentially taking a model beam, which we call Gaussian shell model beam, and mathematically the correlations are given by this equation, where we have two Gaussians. One is Gaussian for the density, which is given by sigma 0 is the width of the beam, in that is the size of the beam, and the other one is the coherence function, which itself is also Gaussian, and delta is the width of the correlation. And one can define a parameter A here, for instance, which is a ratio of these two, and the maximum value of A is given by fully coherent field, and zero value given by incoherent field, and any intermediate value gives us the partial coherence of the beam. So this is how we can plot it, and you could see that we can have higher coherence when A is very high, and zero coherence when A is zero. And it has several applications. So we use this as a pump for our experiment, our proposals. And this is one of the thing which we wanted to study when we do SPDC process, that what happens if we, instead of using a coherent pump, we use a partially coherent pump. So what will happen to the photons here? So what we are doing here is that we have a partially coherent pump beam, and it is passing through a nonlinear medium. This is the SPDC process. We have signal and idler, and we are passing through these beams through double slits in order to see the spatial coherence properties of these beams. and these are the results. Deltas are the correlation, the coherence length of the pump beam, which essentially gives us the coherence property of the pump. So larger delta means more coherence, and lower delta means less coherence. So you could see that in case of coincidences, there is no modulation when the coherence is very low for the pump, and as it increases, we start getting these modulations. That means the interference increases, and we have more and more interference if the coherence is more and more. So that means that the coherence propagates from in this nonlinear process from pump to the diaphragm also biphotons. And if we do that experiment even for long different parameters of the slits, you can see here that the biphoton visibility is less when the pump coherence is less, and it increases and gives maximum, and exactly follows the same laws of classical optics which we already know. So that means that the coherence property can be utilized to control the coherence of the pump of the photons which are generated in this process. Now the question becomes, what happens to the polarization entanglement? But first of all, before going into this question, we would like to explore why we need to do that. So we know that these photons, or the single photons or the entangled photons, we need to travel through atmosphere, through atmospheric turbulences in order to communicate with third parties. For example, in case of quantum communication or quantum distribution. So if we want to travel them through free space, we would like them to have more robustness to atmospheric effects. And as we know from classical optics that the coherent beams, fully coherent beams are much more prone to these disturbances because they are propagating in single mode, and they have more coherence, so they produce speckles and do not reach the detector because of these aberrations. Whereas in case of a partially coherent beam, as you could see that they are propagating in multi-modes, and they have low coherences, and that's why they do not interfere with each other, and then their probability to reach the detectors is more. So we want to use our photons to have such kind of spatial coherence properties, and in order to do that, we need to use this SPDC process with our pump to be having different coherences. And as we have just demonstrated that if we do so with our pump, our biphotons will also have different spatial coherences. And as already recorded by several
कैसे नहीं जा सकते हो मैं
scholars,
कैसे जा
such
सकता
kind
हूँ
of
मेरे से
photons
ज़्यादा
can
रिजर्विंग
be
आप हो
produced
हाँ तो आप जाओ ना
different
आपके लिए
with
कैसे
more
वही
robustness
कैसे
इसलिए
किया
मैं तुम्हें
less
सोचने के लिए
limited
बोला कि कैसे
effects,
मैं
and
कैसे
will have more
जाऊँ
पीएचडी खत्म
probability to
करो
reach the
जल्दी
detectors.
इतने
कैसे
सारे
कर
पेपर
पाऊँ
हैं ऑलरेडी
So,
इतने सारे पेपर
so
में
we
पीएचडी खत्म
first
हो तो
try to
कौन देगा
explore
पीएचडी
what
के लिए लोन
happens
नहीं
when
लेगा
we have
पीएचडी के लिए लोन नहीं
we
लेगा
pass our pump
वो
beam
सब ले
through
लेंगे सर
a
वो कॉन्टैक्ट है वो
video
बहुत
crystal,
पता
which
चल
is one of the
ये
nonlinear
कर लेगा
crystals
सर
for
सर का
generating
बहुत
ताइवान
such
वाला
kind
सारा
of
है वो ताइवान
biphotons.
में तो पीएचडी
And these are
नहीं
the
लेते सर
biphotons profiles
के
when
मेरे
our
टॉपिक
pump
से
is
मुझे नहीं है
potential
आपके टॉपिक
coherent.
से
We are
मुझे
controlling its
तुमको
coherence
बड़ी बड़ी
property as well as its
यूनिवर्सिटी
size.
वो मैथ
So
वाला
these
है
are the omega refers to the size, sigma this is the
नहीं वो
luminance
मैथ
density,
करेगा वो मैथ
and
करेगा
L
वो
is the
मैथ से
coherence.
फिजिक्स में अप्लाई
So you could
करेगा
see that
एग्जैक्टली
when
सेम ही
the
था
coherence
नहीं वो
starts,
प्योर
the
मैथ है
profile
उसके
is very
डिपार्टमेंट
very
में मैथ
good.
है तो मैथ चल
And
जाएगा मुझे
as we
करते हैं
decrease
हाँ
the
लेकिन
coherence or
मैथ
increase
पे फोकस
or
है
increase the
केमिस्ट्री
beam
वाला
size, you could
कौन
see
सा
that it becomes more and more
उसका एक
asymmetric
प्रोजेक्ट
and
मैथ
more
वाला
and
था
more
ठीक है ना
widespread.
उसके पास जाना नहीं था
And that is
उसके पास
true
आया
for
था मैंने कर दिया
both
उसने लिया भी
type
नहीं
1 nonlinear case as
उसने
well
कुछ
as
बोला
type
भी
2
नहीं मुझे बस बोला
quantum
कि नहीं
case. So
होगा
these are the two types of the SPDC process. So as you could see
केमिस्ट्री
that
भी
if
डिपार्टमेंट
we
में
want to use
हाँ
such
ठीक है
kind
तो
of
उसके पास मुझे जाना
photons,
भी
we
नहीं
want
था
to select
लेकिन
the
कर
मेरे को
दिया
क्या
criteria.
था ना
हाँ
मैं
कर
भी
दिया था
कर
मेरे पास कहीं ऑफर नहीं है तो मैं करने में क्या जा रहा है
In
तो
case
ताइवान
of
में भी कर सकते
what
हो
type of
नहीं ना
coherence length we
क्यों
need,
ना
वो
so that we do not
जर्मनी
have
का
to
है
have
एलएमयू का
asymmetric
है कुछ
coherence,
तो होना
and we
चाहिए
have
उसके पास
sufficient
और
partial
उसका प्लान
मैं
coherence
जा
in order
सकता
to
हूँ
have
तुम नहीं जा
robustness
सकते
against free
तुम्हारा
space
स्टैंडर्ड हाई
propagation.
है मैं कहाँ भी जा
मेरे पास
सकता
We
टाइम
will
हूँ
है
also
अभी
experimentally explore
मैं अभी
these
स्टार्ट
different
किया अभी
SPDC
मैं
properties
प्रॉपर अप्लाई भी
when
नहीं
we
किया
are
मुझे मिल गया
passing
रोना आ रहा है
through
मुझे प्लान
तो
था
कब से रही हूँ मैं
ground
यहाँ से
glass
निकलना
plates,
चाहता हूँ
निकलना
passing
चाहता हूँ
them
लेकिन
through
अप्लाई नहीं किया ना
atmosphere
प्रॉपरली जैसे
most
आपने किया था मेरा
probably
प्लान था
asymmetric
कि अभी नहीं हुआ है
effect,
कहीं
and
सबको
also
मेल
कब
लिख
नहीं
दो
आपने
multiplying charge
मेल तो काफी
coefficients
किया ना
UCC,
नहीं होगा
which is actually having
फिर भी
single
लोगों तो
photons as
किए
well.
हो ना
मतलब
And
जितना
you could see
करना
here these
चाहता
are
हूँ
the
जितना
Exactly.
आपने किया
biphoton
उसके लेवल से कम किया तो मेरा
लेकिन
प्लान था
मुझे
कि मुझे
मिल
करना
नहीं
था
रहा था
and we
इसलिए
are
मैं नहीं किया अगर मिल
controlling
जाता
the
तो
मुझे
luminance
क्यों
length
वे
which
सारे
starts varying
ऊपर
from
ऊपर के
space to
लेवल के
space.
किया उसके
You
बाद
could see
आप
that
मुझे भी
in
ऊपर के
order to
लेवल ही
start
करने हैं
getting
ना
more coherence
प्लान
from
वही था
the
कि सबको
fire,
करूँगा मैं
we
ऊपर
have
वाले लेवल
smaller
पे
तो
छोड़
इसका
दिया
मतलब ये तो
area
ताइवान
which
नहीं
is very
जाना है ना
clearly
मुझे इसका
observable.
मतलब ये नहीं कि मैं
However,
ताइवान में ही
it
मिल गई
becomes
इसका
more and more
टाइम से
fuzzier
मिल
as we decrease the coherence
तो ही है
property.
तुम
मैं
नहीं
बस
जा सकते
बता
तो
रहा हूँ
Here
नहीं
कि
तुम
we
जहाँ
have
जहाँ जाना नहीं
used
पसंद
the
करोगे
most
तो
of
तुमको वो चीज़
experimentally as
दूसरों को
well.
रिकॉर्ड नहीं करना चाहिए क्योंकि
We
तुम भी
then
और
thought
चला
that
रहे
okay, let's
आपका
नहीं
सिचुएशन
समझ
अलग
रहे
है
हो
मैं आपके
कैसे
हिसाब
अलग
से
है
बोल रहा
मेरे
हूँ
से
आपका
देखो कैसे
पीएचडी
अलग है
ऑलमोस्ट
and
ओवर हो गया।
entanglement
कहाँ
limits to
ओवर है? दो
explore
साल
here
में लोग
with
PhD हो जाते हैं बिना काम किए
this
हुए।
kind of
कहाँ
काम है
किसने
आपको,
कहा?
इतने सारे काम,
and as
इतने
you
सारे
know that
काम है।
each
कितने
of
काम
these
चाहिए
क्या
आपको?
बोल
crystal
रहे हो
is
भाई?
generating
क्या
one
बोल रहे
ring,
हो?
इतने
and
काम
since
चाहिए
they are
आपको?
having orthogonal planes, their optic axes are orthogonal,
कितना
they
पेपर है,
देखो,
explore
कितना पेपर
the
है?
देख
opposite
इसे क्या
temporal
मतलब
length.
है जो खुद
And
पे
because
अपने
of
ही
this
समझ जाते हैं, दूसरों की
fundamental
अपनी नहीं
overlap,
समझ। और
we want to
ज्ञान तो
select
तुम जब
the
दूसरों का एडवाइस
photons
दोगे,
for
तुम्हें उस
which
जगह
are
नहीं जाना है,
having
लेकिन दूसरों का
polarization
एडवाइस देना है कि
region
वहाँ जाओ। ऐसा कैसे कर सकते हो? तुम्हें जो चीज
entanglement.
पसंद
You
नहीं है
see
तो
that
तुम
the
नहीं
polarization
है।
region
आपको जबरदस्ती भेज रहा हूँ क्या?
नहीं तुम
मैं जो
आप
बोल रहा हूँ,
बोल किससे
and the
सकते हो?
reason
क्योंकि
being
तुम्हें खुद
that
ही वहाँ नहीं
with
जाना है, तो तुम
increase
दूसरों
in
को बोल
spatial
ही नहीं सकते ना।
coherence, the basically
नहीं बोल
सजेशन
सकते।
ऐसा कोई डिफरेंस नहीं
अरे
पता चल रहा है आपको।
सजेशन ना अच्छा सजेशन देना चाहिए। सजेशन किसे बोलते हैं? जो
so
जिसके
in
लिए
order
वो
to enhance the
फायदेमंद
entanglement,
हो।
one
मतलब
possibility
तुम्हें
is
वो उस जगह
सजेशन
जाना
और
है।
साइंस में फर्क नहीं पता चल रहा है।
and
मैं आगे आपको जबरदस्ती भेज रहा हूँ।
small
वो बात
apertures
नहीं
मैंने
बोल
आपको
सकते।
जर्मनी का सजेशन दिया, वहाँ पे पीएचडी मिल गया ना, एक बार थैंक यू
they
बोला
are
आपने।
reducing the
नहीं
aperture
आप
sizes.
हमेशा
They are
बोलते हो
reducing
ताइवान चली जाइए, अबू धाबी चली
and as the
जाइए।
aperture size is
मैंने अच्छी जगह में
smaller,
सजेशन दिया, जर्मनी
अच्छा
में आपको पीएचडी
वो
हो गया।
है ही
is
कौन
to
सा? उसका
visible,
रैंकिंग
and you
पता
could
है?
see that the
1100
entanglement
1300
नहीं
even
इतना
for
नहीं है।
very small aperture size, you could see
काले
that
रंग
the
का
हो गया
entanglement
ना पीएचडी?
remains
कहाँ हुआ?
very high
उसने
value,
इसने
कहा
हाँ बोल दिया ना।
हाँ बोलने से
even
होता है।
violate
हो
the
गया तो और
density
क्या
of
चाहिए?
this.
तो
So this
पीएचडी
is
का काम हो
tropical
गया, ऊपर
aspect,
से
and currently we
रोमन
are
बना
doing
रखा
those
है।
experiments. So these are some of the experiments which we are having. For example, these are the SPPC experiments for entanglement generation. So this is the polarization entanglement.
ठीक है, हो गया ना आपके
This
पास?
one
बैकअप हो
lab
गया
which
ना?
is having a visibility
नहीं
of
उसको नहीं किया है
about
दे देगा।
5%,
एक बार हाँ
and
बोल के
our
कोई ना कोई बना
और
देगा।
नहीं किया है।
single photons are of the order of 1000 and 2000.
Bhaskar, just
Yes.
hello.
Yeah. Can you hear
Yeah,
me?
just to give you a sense of time, you have all total 15 minutes.
Okay, so I'll
Hello?
maybe in 5 to 7 minutes. Perfect.
No, absolutely. Go ahead. I mean, choose as you like. I just wanted to let you know.
Yeah. Because I have
exactly.
some interesting
Yeah.
things to show
Please go
again.
ahead.
Yeah. So the other
Yes,
source,
sure.
the other source which we are showing here is a similar kind of source, but it has a different geometry. It is also an entangled photon source, but at the time you could see here that it is using a Sanya kind of interferometer, and the crystal which we are using is no longer a paired video crystal, but it is more of a periodically cold non-linear crystal where the length could be increased significantly. So here it is roughly 30 millimeter crystal, and the rest geometries are slightly different, and what we get here, we can see the visibilities. So these are the polarization visibilities in H and E,
टॉप 10
for
में तो दुबई
example.
आता नहीं है।
And the brightness of this source, as it is much
Top 10
more
cities में नहीं
efficient,
आता
is
है।
11 megahertz
यूरोप
per
की cities आते हैं।
so these many photons pairs we are getting 11 million pairs per second with 1 milliwatt of link power. So it is a very efficient source, and currently we are trying to use it for generating entanglement, because this is so far a single photon source, and this is an entangled source. And here, as the rates are very high, they are very efficient and very much useful in the area of free space computing, where one needs to have higher rates for
ये
higher
गूगल में
generation.
अभी रिसेंट में टॉप में
So now I will just summarize some of our activities in the area of quantum distribution. I believe we all are aware about QIQT, where the goal is to communicate with legitimate parties with absolute security. Even there is existence of Eve, but in quantum domain one needs to identify when Eve is attacking into the system or trying to eavesdrop in the system.
टॉप लिखा ना, मैं 10 नहीं लिखा हूँ।
The quantum principles, and here we are using different photonic freedoms, degrees of freedoms in order to do so. For example, the quantum channel, our photons can have a polarization qubit, which is basically horizontal, vertical, as well as their superpositions. You see all superpositions are possible. We can have an orbital angular momentum kind of qubit, which is another property of photons, and we can have L minus L and their superpositions. And we can also have a vector where we have photons arriving
ये अभी recently
the arrival time of
फिर
photons,
second
and
time
then
इसको
we
तो
have
पहले कितना
photons
है
arriving early or arriving late, and their
मैं
propagation. So any of the properties we can
वो
choose.
पैसे को कितना पैसा मिलता है?
So we have been first interested in the phase property of, to realize quantum distribution. So this is basically the phase of, so what we do essentially, we use a 1-bit delay interferometer, which is shown here, and this is one developed in our lab. This interferometer essentially interferes pulses of light and these pulses are obtained from a continuous wave laser by modulating the intensities and giving them random phases
ओके
by the
अच्छा
phase bulb.
उसके बाद है
So
क्या देगा
this
टूरिस्ट बताओ
these one pulse interferes with its one bit delayed
वो
copy,
बता देते हैं
and as you could
आगे
see
नहीं
here that only those events when we will have photons first of all would appear, and they will appear when there is a bright pole and there is a dark pole,
इंडियन
as
से
we
करना
mentioned in the
है
previous
इंडियन
talk
से
as well.
नहीं
And depending on the phase of the interfering pulse, one can choose to land it either in the bright pole or in the dark
में
pole.
तो
So Alice has
चोरी
the
होगा
control of this phase. She knows that which photon will go to which port. It's the Bob who gives the information to Alice that where which port has been, what time stamp of the detection has been, and from her data she can actually acquire the information, and that way both can
रूम
settle the
देखो
game.
रूम
So this
देखो
is called a differential phase shift quantum key distribution, and it has been a very,
छोटा है
very
आपसे
powerful
छोटा
way
होगा आप जो
to
मैजिक
complicate
करोगे
to set up the keys between Alice and Bob.
मुझे नहीं पता लेकिन तो
So
बता
in our
देते
lab, we decided to do that, and since the semiconductor-based detectors had very less quantum efficiency, we decided to
लेकिन
do a
मतलब रूम
linear
तो काफ़ी छोटा है
superconducting
उसका रूम
detector. So
में
this is a
खिड़की भी नहीं है
superconducting nanowire single photon detector in our lab, where we have a quantum efficiencies which are more than 85%, which are 8.5 times larger than the normal detector, semiconductor-based detector, and also our direct times are very, very low, about 50 second, nanosecond, or even less, so that we can have more and more detection of photons. So we decided to do this BPS QKD with this kind of speed. So we are starting with our laser having 2.5
ये
gigahertz
जूम
pulse
चला
rates.
होगा
This is the phase modulator.
कनेक्ट कर दिया
They are attenuated to
आज
less than 1 photon per pulse, and then they pass through a fiber spool in our lab, which is about 150 kilometers. This 1 bit delay interferometer is used to detect the photons at different ports, and
यूनिवर्सिटी
the
में
superconducting detector with time tagger gives us
एच
the timing
पॉट
information.
ट्रस्ट
So as you could see here, with a rate of 2.5 gigahertz,
एच
our
पॉट
Cooper quantum bit error rate, which is essentially a measure of how how much error is in this process, was about 13%, and the shifted key rates after this process after this quantum channel of 150 kilometer fiber were about 100 kbps. So this was a lab-based
हांगकांग
experiment,
यूनिवर्सिटी ऑफ
and as you could
साइंस
see that the qubits were slightly higher side, and still that has a potential to be implemented in any metropolitan kind of network because the distances involved were quite high. Well, still the problem of this QBER was basically coming from the fact that we were working at a very high rate, and we do not had such kind of equipments which could actually give proper phase to each pulse. So we decided to decrease the rate so that we could decrease the QBER. So this is our another experiment where we went to a rate of 800 megahertz, which is way lesser than 2.5 gigahertz. And what QBER we achieved was about 4 to 6% only, and the shifted key rate with 100 kilometer fiber were more than 15 kbps. So this is the experiment where this 110 kilometer fiber was having a pair fiber as well, where we could actually synchronize this Alice and Bob through a FPGA system. So this was exact replica of what we wanted to do in the field. So we decided to take these setups in two end stations. One was at Prayagraj in UP, and the other one at Vindhyachal, and they had the telecom fibers which were separated by 100
आपसे तो बात होते रहता है इसी
so
पे बोलना है
these are the commercial fibers which are available with a loss of about 26 dB.
पूछ लो
The
आके
transmitter was
फालतू की बातें तो होती
at
है
Alice side, and the Bob
कर
was
दो
at
मैसेज
the Vindhyachal. So these are the results which we
फॉरवर्ड
achieved
कर देना
here.
मैं
So
मैसेज
this
कर
was
दूंगा उसको
a
फॉरवर्ड
joint
कर
effort
देना
first of all for with IT Delhi and
बीपीएस
DRDO.
100
And
किलोमीटर
we have been using 100 kilometer channel, which was the first long range demonstration. The losses, the QBER, what we achieved were about 9%, less than 9%, and the shifted rate about 10 kilohertz. And we had used FPGA based clock synchronization between transmitter and receiver, that is also through the fiber. And we believe that this is one of the experiments which is a stepping stone for future quantum networks and quantum internet. And in fact, by multiplying these trusted nodes, one can actually set up longer distances such as 2,000 kilometers or even more, connecting two or more cities.
मतलब
In
ये
fact,
हो
in
गया
the lab, we
हाईएस्ट
are
समझ लो
also
कि जो सबसे
doing experiments where we could utilize entanglement for QKT. So this is one of the scheme which we are currently working on, where we wish to demonstrate QKT between two end stations with fibers, but using an entanglement process, and then use some of the not only to show the entanglement distribution, but also using one of the entanglement based protocols, and it will be going to be a test bed for these kind of experiments.
ठीक है,
This
32
is
लाख
probably my
का
last
तो हो
slide.
सकता है फर्स्ट ईयर में
On where I would
दूसरा
like
प्रोग्राम
to
है जिसको फर्स्ट ईयर
actually
में
focus on the fact
हम देते हैं
that since we are currently working at telecom wavelength, we would also like to use that wavelength for free space.
5000
The reasons are listed here. So first of
In
all,
the first
there
year.
is the same wavelength for free space and fiber, so it would be good to integrate systems using both the QKTs. The detectors have very high quantum efficiencies, as well as the processes are more efficient for telecom wavelength. We can use both day and night time propagation because the solar spectrum has very
ऐसा
small
40 को 12 से डिवाइड कर रहे थे 50 से डिवाइड कर रहे
also
हो
has noise, and also it is not visible to human eye, and that is of statistical
नहीं नहीं
importance.
पर ये
And as our
41,000
free
पर ये
space has
4,000 नहीं
similar transmission parameters for 1550 as is for 800, which is currently used for such
हाँ
communication.
मतलब ये
We
और
can
एक
use
दूसरा है
such
जिसमें
kind
5000
of
पर ईयर
wavelength
मिलता
for
है
these kind of QKTs at telecom wavelength for free space communication. So I would summarize that we discussed, we started with coherence and polarization properties of light in the classical optical. We have shown that how we can make tunable DOP and DOC video polarization and coherence in sources. We demonstrated polarization difference theorem. We have also shown that how polarization and partial coherence can be used for controlling the entanglement property of light. And finally, I discussed the quantum state engineering, development of single and entangled photons, and also to use them for QKT schemes by developing several QKT schemes and demonstrations. I would like to thank the funding agencies for their support, and our group at IIT Delhi, which includes some postdocs and
60,000
and master students
में
who
जाता
have been working hard in the labs
60,000 नहीं देता
for
क्यों देता
realizing
60,000
experiments. So thank you very much for this time, and I would like to take questions now.
60,000 वो हांगकांग में बता रहा होगा
Okay. Bhaskar, thank you for the wonderful talk. Particularly, I mean, at least I was not aware that there's a lab in which both classical and quantum optics is going on parallelly. It's wonderful to see that such developments are there.
Thank
And
you.
state of the art experiment. Yeah, congratulations to you for the work and updating us. Yeah. Now the time. Can you please raise your hand if you have a question? Or you can unmute yourself and ask. I can't believe that nobody has a question.
Nobody understood.
No, I think they are probably mesmerized by the wonderful experiments you are doing. Yeah. Okay, I'll wait for one more minute. If nobody is willing to ask questions, I have really quite a few questions, but I'll ask one and maybe communicate the rest to you over email.
Yeah, sure.
पोस्ट में क्या क्या होता है I don't get what you mean.
But you can ask a question in between by the time others raise hand. Yeah.
Okay. Okay, Bhaskar, going back to this parallels between quantum mechanics and classical, I got a bit confused there, so maybe I'll take you back there. You had this slide where, there was this number of things added up to the, I think, polarization, right?
Yeah.
And then there was this question of parallels between the complementary principle in quantum mechanics and the classical domain. So I think so, maybe I explain how I am understanding. As you are trying to, so you're basically saying that if you know exactly which path the light took in physical space, which means it's kind of being squeezed down and it is a 1D path. When you think of a path, it's a one-dimensional trajectory essentially. So as I'm squeezing down the light to travel along a one-dimensional trajectory, that is what you call particle light in the classical inference. And when it's completely spread out, you're probably calling it I mean, wave-like. Is that correct? Is that the classical, on the classical side, is this the?
Well, I mean,
And then, of course, you are looking at a duality between the two.
yeah, so basically, let's consider the Young's experiment. We have two slits, lights are passing through the slits and they are interfering. Now, let's forget about quantum for the moment, and we just want to see what happens to the interference. We have two beams which are interfering and we are getting the fringes. The measure of, so the fringes are coming because of the wave nature we know, and the quality of interference or the quality of wave nature can be given by the visibility of these fringes. That is the only measure by which we say that how good are the two beams which are interfering. And we see that the visibility is maximum when the two beams are not distinguishable. That means that the intensities are the same. That we already know from classical physics. And now if I increase the intensity of one beam with respect to another, I am actually decreasing the visibility and the interference becomes less and less, having less and less contrast. And there will be one point when there will be only one beam remaining, there will be no other beam and there will be no interference. There will be only that beam falling at a particular position. So what is happening now? We were in the wave nature, we were showing interference to you, and now suddenly I started to play with the intensities. That means the which path information. I increased which path information in one arm with respect to another, because if I put detectors out to clearly distinguish that which path has more intensity with respect to another. And there will be one point when there will be only one path remaining. That means I am 100% sure that the beam is coming only from this path. So that means that there is only particle picture now, means which path information is there, but there is no interference. So this is just an analog. It is not exactly the same, because when we talk about quantum physics,
that is the sense. No, I'm just trying to catch that.
I'm not saying
I was
that.
trying to catch the sense in which you.
Yes. So why I was saying is because if you see nowadays, people
I
have
got
done
the point.
with the non-separability of light, for example. It is not exactly quantum, but it is something which has been seen. In quantum physics, we know that randomness is its nature, but it is defined as random. But in classical physics, it is our ignorance to have it random. We can actually define everything perfectly.
Okay, thanks a lot. Any other question? Okay. If not, Bhaskar, thank you again for the wonderful talk.
Thank you very much.
And so we hope that next time we host you physically.
I'll be happy to talk about some new aspects next time. Thank you.
Sure, absolutely. Thank you. So we move on to the next talk. I think I hand it over now to Professor Panigrahi, or the organizers, who supervise the organizing team.
Hello. Yes, sir. Panigrahi sir soon join. He's not here right now. Hello.
Yes, I am here.
Yeah.
So,
So I introduce you